Okay.
All right. Well, hello, everybody. My name is Vicki Knoer, and I am a third-year graduate student at the University of Colorado in Boulder. I study aerospace engineering, and I am working on my PhD project, which is to build a rocket payload, which will be launched from Alaska in 2024. And we will spend a few minutes observing the sun with a spectrograph while we're in flight, and then we'll come back down land and go pick the rocket up. I haven't always been doing aerospace engineering. I started out in environmental science with a degree from the University of Kentucky, and then I switched over to physics and astronomy from the University of Louisville. So I am here. It's great meeting you all, and I am here to talk about how satellites work and what they do and all the different systems that go into making a successful satellite. Let me go ahead and start this slideshow. Before I start, does anyone have any questions before we're starting this?
When you start your slideshow, if you guys have any questions, you can put them in the chat also if you don't like to speak out loud, and then I'll relay them to Vicki. And because you probably won't see the chat if you have your slideshow up.
Yeah, thank you.
Okay.
Okay, so how do satellites work? As I mentioned earlier, I'm a grad student studying aerospace engineering. I've studied environmental science and astrophysics already, and I'm helping to build a rocket payload. These two images on the right are similar to what I'm working on, but those are not that's not my rocket. My rocket is still in design, so it's mostly just on the computer at the moment. We haven't started purchasing anything yet, but we're hoping to start buying stuff and actually putting stuff together soon. Now, satellites. I have been studying satellites for about 2 years and taking a lot of classes in how they work. So I figured some of you might be interested in learning a little bit about how they work. Today, we're going to talk about what they're used for, what are the different parts or systems of a satellite, how do they work. So we're going to talk about communications, power, heat, navigation, pointing, and data management. And then I'm also going to cover how anyone here can be a scientist or engineer. I'll start with what we use satellites for. And we have all sorts of stuff that we use them for. The primary one that you probably interact with is GPS. This will track stuff for your phone. It can track GPS in cars. It is also used by airplanes for their location tracking. We also use satellites for communication. Satellite TV is the most obvious one there. But we also, they will occasionally route cell phone calls from the receiver, from the big cell tower up to a satellite, to another satellite, and down to a receiver somewhere else on the planet. So sometimes they will carry cell phone communication as well. Additionally, we have weather satellites to measure air and ground temperatures. We use them for storm tracking as well. We have lots of scientific data satellites. We can use those for investigating plant coverage or figuring out pollution. We have plenty of space telescopes. Those do count as satellites. And I mentioned that we watch solar flares on satellites. Those are a bit more difficult to watch down on the Earth because the atmosphere gets in the way. So we have to put stuff in space to see them. And I mention that because that's what we are hoping to see for my PhD project when I launch. Finally, we also have satellites for military purposes. There are plenty of spy satellites out there, and I don't know about them, but I imagine there's probably also plenty of weapons satellites because that's how the government is. So satellites can come in all sorts of sizes. They can range from communication satellites and big NASA telescopes, which are as big or bigger than a bus, all the way down to CubeSats or cube satellites, which are about 10 inches by 10 inches by 10 inches. So about completely hand-sized. And those are more used for climate research applications, technology demonstration, because we want to test something small and easy before we send it up and test something big and difficult and expensive. And also lots of school projects. There are a number of grants out there to fund schools to actually have the students themselves build CubeSats, and then NASA will offer rides on some of their launches so that the schools can send them into space. You can see some of the satellites in these pictures here. We've got a replica of the Hubble telescope up on the right, top right. On the bottom center, this is a communications satellite for Maxar. It probably carries a lot of TV signals. And on the bottom right, that is that's a satellite called the NASA PhoneSat, which I forget what it does. It's probably a technology demonstration mission. So what are the different parts of a satellite? All the different parts of the satellite are grouped into subsystems. That includes the power subsystem, which usually has solar panels and a battery. Navigation, which includes thrusters, momentum wheels, and pointing cameras. We've got communications, which is usually a receiver and a transmitter. We've got the payload, which is usually the science part or the communications part, if it's one of the big communication satellites. There's the thermal subsystem, which handles heating and cooling. The data subsystem, which is the processor, the memory, everything, all the computer stuff that makes the satellite run, and about half a dozen more small subsystems. So how does a satellite know what to do? Well, first off, we can program satellites ahead of time, but there's a limited amount that we can actually program them. And we're starting to develop artificial intelligence so that they can start to run themselves, but it's not very advanced yet. So they do still need regular communication with us. So what we do is when the satellite passes overhead of a receiver station, and I've got a little image of a satellite dish here, we tell the satellite dish to send days or weeks worth of commands to the satellite. This is S-band radio, which is a 2 to 4 gigahertz signal for anyone who thinks radio communication is really cool. So we send up all of our commands to the satellite, and at the same time, the satellite sends down all of its data that it's been collecting over the past couple days or little while. The satellite will receive it through its little bitty receiver dish. It will incorporate all of the commands into its own processing, and then it will usually pass the ground station and keep going. Then once it comes around again, because it needs to be within view of the satellite dish. Once it comes around again, we have another opportunity to communicate with it, send up commands, receive data back down. Now, power subsystem. You all are fairly familiar with how satellites get power in that we use solar panels. These are pretty much the exact same solar panels that you see on top of houses, out in fields. It's pretty much the same technology. And while the solar panels are pointed at the sun, we're gathering energy. That energy is stored in the battery. And I have an example on the bottom right here. This is a rechargeable battery and basically works like a car battery. From there, the computer decides how everything is powered and then sends power out to the electronics and the instruments, the payload, to run the satellite. Heating is definitely a difficult problem in space because, yeah, space is cold, it's very cold, but there's no air, which means it's very difficult to actually cool off. If we don't have air touching the satellite to actually physically carry the heat away, it has trouble cooling off, and the only option it has is radiative cooling, which is the same as if you're standing far away from a fire and you put your hand up, you can feel the heat on your hand, even though the air next to you may not actually be hot. So some sources of heat that we have to deal with include the sun, because the sun makes a lot of heat. Batteries, when you use a battery, some of the energy is turned into waste heat, and we have to figure out how to deal with that. And then the electronics, while they're running, will also heat up. Sometimes that's good, sometimes that's bad. If we have too much heat, we can radiate it away into space with a radiating panel, like you see up on the right. That's basically just a big sheet of something that sticks up and is hot, and then it will have heat in the form of infrared energy radiating away from it into space, and that's how we can get rid of that. If we are worried about big temperature changes or keeping something warm, we can use multi-layer insulation blankets, which you see down on the right, on the bottom right there. It's basically a whole bunch of fancy plastic and aluminum sandwiched together to make a blanket for the spacecraft. And we literally wrap things up in this to keep them warm. Finally, if just the energy from the detectors and the batteries isn't enough, we can also slap a heat pad onto something and plug it in, and that will keep that instrument, that will keep that board or panel also warm. And you can see that in the middle here, we've got a thermal heating pad. Do you have any questions so far? Over thermal, power, or communications? I'm going to take that as a no and go ahead and move on. Heat protection. So one of the crazy ideas that they've been sending out that you guys are probably going to hear about a bit more in the next year is the James Webb Space Telescope. So the James Webb Space Telescope views things in the infrared. And to do that, it needs to have all its surfaces, its detectors, its mirrors, everything need to be very, very cold, almost at the temperature of the rest of space itself. Now, the problem is it's going to be orbiting and it's just going to be sitting in the sun. And all this sunlight is really, really going to heat it up, which will make it much, much too warm for what it needs to be able to observe. So scientists developed and engineers developed this really cool sunshade to protect it from the sun. It's basically like a big umbrella that protects you from the sun. So you can see right here, there's 5 layers of an aluminum fabric, and NASA actually has about a half a dozen people who can sew, and they have fancy sewing machines, and they literally hand sewed all of these blankets together for NASA. So if you like to sew, you could sew for NASA. Anyway, they sewed these blankets together and they set them up in this, they set them up next to each other. And each of these blankets is protecting the telescope from the sun. So the sunshade, the first sunshade here on the bottom where the sun is shining, it gets hit with all the solar radiation and it heats up a lot. So it blocks all the sunlight, but it heats up a lot and it gets very, very hot. Then the blanket next to it, the job of the blanket next to it is to try and block some of the heat from this first sunshade. So the second sunshade blocks the heat from the first and gets not as hot, just kind of hot. Then the third one does the same, blocking the heat from the second, and only gets a little bit hot. And by the time you get to the top sunshade here, it's not getting hot at all. So this telescope is completely blocked from the heat of the sun. Now, pointing and figuring out where the satellite is and where it's pointing can be a pretty big challenge, because you can't just take a picture. It's pretty difficult to just take a picture of a satellite and say, hey, satellite, you're pointing this direction, you're in this position. We can figure out where it is and tell the satellite where it is, but once it passes over us, we can't communicate with it anymore. So it actually has it has the ability to make orbital calculations on its processor. We tell it where it is, and it uses orbital mechanics to figure out how long it's been traveling and use gravity and its orbit to figure out where it is at any given time. Now, there's always going to be slight perturbations. That's not going to be a perfect solution. And so its orbit will change after a couple orbits, and we want to update that. So occasionally when it goes over the ground station, we will give it some new information on where it is, and it can update that and fix its calculations. So that's how we figure out where it is. But how does it know which direction it's pointing? It uses, the primary way we do this is with two different instruments, one called a sun sensor and one called a star tracker. So on the top right here, you can see a sun sensor, and it basically tells us, hey, is this camera pointing at the sun? Yes or no? And if it is, cool. If it's not, then we know the sun's not in that direction. So you can see this is basically a cube here, and each of these two little dark detector boards, those are our sun sensors. So if the sun is, whichever one the sun is shining on, we know this computer will know that, oh, that's the direction that the sun is. Additionally, we have star trackers, which that's this camera, little camera and telescope on the bottom right here. It's a small camera that is designed to look at the stars, and the satellite in its computer has a star map, and it can actually figure out which stars are which that the star tracker is looking at, and by figuring out which direction the star tracker is looking and at what stars, it knows which direction it's pointing. Once it figures out which direction it's pointing and what location it has, we might want to move it. So we use thrusters for, we can use thrusters for moving and reaction wheels for spinning. Large thrusters, like the ones on the bottom left, can help the satellite move around in orbit or move into a different orbit. Those are the big ones that take the satellite from here to over here. Now, most satellites aren't big or fancy or expensive enough to have thrusters on it. Most of them will just get put into an orbit and exist there until they slow down and fall into the atmosphere. Only the bigger, fancier satellites have thrusters to actually move around. Some satellites will also have rotational thrusters. They're little thrusters on the edges, on the corners, that when you turn them on, it makes the spacecraft spin in one direction or the other. And we can use this to rotate the spacecraft. Additionally, for rotating the spacecraft, engineers have come up with a very clever method for rotating just a little bit, or just exactly right. And that's called reaction wheels. Reaction wheels use the principle of conservation of angular momentum to figure out, to keep the spacecraft moving exactly how they want it to and spinning exactly how they want it to. So if I've got, let's say if I've got a satellite with a heavy wheel and it starts to spin counterclockwise, because we need to conserve angular momentum, I start to spin this clockwise or counterclockwise, and my spacecraft will actually start to rotate clockwise to make up for it. So we can control how the wheels spin, and by extension, control how the spacecraft is spinning using the reaction wheels, which, in my opinion, is probably one of the coolest things on the spacecraft. So finally, data. Everything else is just upkeep. Everything else is making sure everything is running, making sure everything is safe, making sure we can talk to it. But the real purpose of the satellite being up there is so we can get information from it. There's a lot of different types of satellites, and they have lots and lots of different types of instruments. I've listed 4 here, but there are dozens more. So these are all instruments that are mainly useful for taking scientific measurements. We've got imaging satellites, which those are what produce Google Earth images. Those are what produce hurricane pictures when you've got storms coming up. And they have cameras that are actually, they just have cameras on them. They're very similar to the camera in your phone or a photographer's camera. So we just get a camera, stick it in a box, stick it on the satellite, and it actually works pretty well, just being from space. Another type of satellite is a LiDAR satellite, which LiDAR is kind of like sonar or echolocation. The LiDAR satellite sends out a pulse of light. The pulse bounces off something, the ground or the atmosphere, comes back to the satellite, and then hits the detectors. And the satellite records how much time it takes for the light to go out from the satellite, bounce off something, and hit the detector. Based on that, we can figure out how far something away is. And that's actually a very similar way to how bats use echolocation, except bats use sound, and this satellite is using light. So you can see what, on the bottom left, we've got a LiDAR satellite, and it has traveled in the path, and it has mapped the distance to clouds in its path. Then on the top right, there are plenty of instruments and satellites that are studying the Earth's magnetic field, because the Earth has it acts kind of like a big bar magnet, where you've got magnetic field coming out of the South Pole, coming up kind of like an apple shape and going into the North Pole. It's the same thing that your compass uses. So that is actually super, super complicated, and much more complicated than just a bar magnet makes it look. And so people who are studying that need to know a lot of very detailed information about it. And so we send satellites always going around the Earth to figure out what direction the magnetic field is pointing and how strong it is at any location. Finally on here, I've got X-ray satellites. And in that, I also include any of the big astrophysics satellites like Hubble or the James Webb Telescope or something. So X-ray satellites have special optics that can detect X-ray light. We usually see stuff like X-ray light from the sun or stars or the center of our galaxy. And these satellites are actually kind of similar to imaging satellites. They do have special detectors and special mirrors that they bounce all the light off, but essentially they're just a fancy telescope that we threw up into space. And on the bottom right here, you can see the Chandra X-ray Observatory, which I think might have been retired by now, but that was one of the the first great observatories that NASA sent up, and it took a lot of X-ray pictures. So we've got a chat message. Recording will be available in a little while. So that is a brief overview of how satellites work and what all the different parts are. When you're on a team building a satellite, you usually have a whole group of people with one person in charge of each of these systems and directing several people working with them to all put this together. So building a satellite is definitely a team effort. Now, I know a lot of you, this is a STEM club, and so a lot of you are probably interested in being scientists and engineers for maybe a career or just as a hobby, because it's cool. If you're interested in this, you should all know it doesn't take school to make you a scientist or engineer. You don't have to go to college and get a fancy degree just to figure this stuff out. What it does take is being curious about stuff. If you want to figure out how things work, that's a great mindset to start with. You can do this once you figure out, hey, here's a question. I don't understand this. I want to understand it better. Write down what you're thinking. Write down how you plan to figure it out. Write down, after you do figure it out, write down whether you were right or wrong and why you may have been right or wrong. Starting a journal like that is an excellent way to practice being a scientist or an engineer and really get you in, teach you a lot about yourself and how you want to keep going with this. Additionally, you can always ask questions. People studying science and engineering love getting questions about how things work. Everybody likes talking about what they do. So it's never going to be a problem if you go and ask how something works or what somebody does for their job. Additionally, if you all want to do actual real science, like actual real life science for actual real life scientists that has actual real life applications. There is something called citizen science, which you can help with research online. They need volunteers to identify and classify images because computers are exceedingly bad compared to people at classifying images. So researchers really need your help to go through a lot of the data. So if you want, zooniverse.org is a website that I really like for this. I've linked to projects in this PowerPoint, which will be sent out later, so that anyone who wants to can try it out. This first link is to help to identify kelp forests using satellite images. And the second one is to go through astrophysics data and find planets around other stars. And these are really easy stuff. It's really looking at pictures and like highlighting or circling things in the picture and saying, hey, this looks like it might be this. This looks like it might be this. Stuff that computers are very great at. And if you want to try engineering, there are probably rocketeering or engineering clubs near you. I don't know what all the STEM science club does right here, but I imagine this is also an excellent place to figure out projects that you can work on. So that is the end of my talk, and I appreciate you guys sitting through it, and I hope you guys found it really interesting. So now, do you want to, were there any questions or anything you found really cool and wanted to learn more about?
Yes. I have a question. How do satellites remain in orbit?
How do satellites remain in orbit? Okay. So when trying to think of the best way to describe this. So imagine I have a baseball and I go out into space and I throw that baseball. Well, it's going to go and it's going to curve towards Earth and it's going to land on the Earth, right? Well, if I throw it harder, it's going to land further away. If I throw it really, really hard, it's going to land even further away. Now, at some point, it's going to land so far away. Let's say this is me throwing my baseball. It's going to land so far away that it actually starts going around the curve of the Earth. Well, if I throw it just a little bit harder, it'll go around and it'll keep falling towards the Earth and it'll keep falling towards the Earth, but the Earth also keeps curving away from it. So eventually, it will always be falling, but the Earth keeps curving away from it, and so it'll just end up being in orbit, going around and around and around. You can also think of this as, so gravity is always pulling stuff towards the Earth, right? But if I have something on a string, let's say a ball on a string, because balls are easy to talk about. I've got a ball on a string and I start whirling it around my head. That string is always pulling the ball in towards me, and that ball is always trying to zoom off into some other direction. And it going around in a circle, it's trying to leave and go off that way, and the string's pulling it in, and so that makes it go around in a circle instead of off in some direction. And gravity kind of works the same way, where the satellite going around the Earth is always trying to leave off in that direction, but gravity is always pulling it back in, so it just ends up going in a circle. Thanks for the question.
Thanks for that. That's interesting. I have a question about high and low orbit satellites. What are the differences?
So there's 3 general types of orbits, but they're not, there's no solid line between them or anything. We like to classify things as low orbit, mid orbit, and geosynchronous orbit satellites. So low orbit satellites, low, middle, and high, basically describe how far away from the Earth you are. A low orbit satellite will be a couple miles above your head, whereas a geosynchronous satellite will be maybe a couple hundred miles above your head. So low orbit satellites are not actually that far away from the Earth. That's where the International Space Station orbits. And that is right on the edge of the atmosphere. The atmosphere doesn't really have a big, it doesn't have a cutoff edge either, but that's pretty much where the atmosphere goes to nothing. So that's orbiting right outside the atmosphere. And that's the closest to the Earth. That's also the easiest to get to because it's the closest. If you want to be looking, like taking pictures of the Earth or doing like taking science images, it also helps to be in a low Earth satellite because now you're closer and you can see better. There are also satellites that there's an orbit called geostationary orbit or geosynchronous orbit, which the Earth makes one rotation in 24 hours, right? If you put a satellite up at a distance where it also makes one orbit in 24 hours, that means you're always looking at the exact same side of the Earth as it rotates. So there's a couple of geosynchronous satellites in orbit around the Earth. There's several above the United States, so they are always looking at the United States. The Earth doesn't rotate underneath them. They don't go faster. They're always pointing at the United States, so they can always see it. And that's usually used for weather information for the US. That one is a very difficult and expensive orbit to get to because it's much, much further away. So you need a lot more rocket power to get you there. Then there's mid-Earth, which doesn't have a specific category. Like there's not anything particularly special about it. It's just not low Earth and it's not geostationary. It's just kind of in the middle.
So is super synchronous orbit, is that a little higher than the geosynchronous orbit, where they like, I guess they call that the junkyard, the junkyard orbit?
Yeah, there is also a junkyard orbit. So one of the big problems facing space right now and in the future is that there's a lot of stuff up there. In addition to all the satellites that we put up, there's all sorts of like used rocket boosters, or when you put your camera up, you take the lens cap off and it just floats away. Or maybe two satellites accidentally ran into each other and exploded, and now there's all sorts of junk everywhere. That's a really big problem, space junk being up there, because the more stuff is up there, the more likely you are to run into something. And collisions up there happen very, very, very fast. So even a lens cap can still tear a hole through something. So that's a big problem. And we're trying to figure out how to mitigate it and how to get rid of all this space junk just orbiting around. One of the ways we do that is if a satellite has large thrusters that it can move around into different orbits, it'll actually run and they'll turn on the thrusters and send it out to a graveyard orbit, which is higher than geosynchronous orbit, because we don't really put anything else beyond geosynchronous. So if we send everything out further and park it up there, then it's not really a danger to anything else we're using. So that we basically use that as a junkyard or a trash yard. Thanks for the questions. I'm also happy to answer questions about like college or what I do, classes. I also enjoy stuff like backpacking and playing card games and board games.
So the satellites that go to this, I always have I love the ones that's way out there. They don't have a tendency to fall back to Earth because they're so far away. They just kind of just float, like people say that these satellites are falling back to Earth, but those are the ones that are pretty much in the low orbit, right?
Yeah, so the only satellites that fall back to Earth and burn up in the atmosphere are the low Earth orbit satellites, the ones that are the closest. This is because once you've got something orbiting around something, it's going to orbit forever unless something else gets in the way. Just like the planets are orbiting around the sun, they're not going to fall into the sun. They're just going to kind of orbit around the sun forever until the sun explodes and gets in the way. So normally when something's orbiting, its orbit isn't going to decay. It's just going to keep its same path. But when you've got a low Earth orbit satellite, like I said, the atmosphere doesn't have a top. It doesn't have an ending point. It just goes from dense to less dense to very less dense. So when you're in a low Earth orbit satellite, you're still occasionally running into air molecules, and it's still very slowly slowing you down. So over time, your satellite's going to slow down, your orbit's going to lose energy, and when your orbit loses energy, it tends to come down in altitude. And when it does that, the atmosphere gets thicker, it slows down more, it scoots down even more, and eventually it'll just tumble into the atmosphere and burn up. Looks like we've got a chat message. Is there a bias against adults that go back to college for the sciences, astrophysics specifically, in the 30s and 40s? I would say no. So a traditional student or a traditional college student is someone who goes straight from high school to college, and if they go to grad school, then they go straight from college to grad school. But increasingly, there are more and more non-traditional students, and that includes people who took a break after high school, people who have families and have to take care of their families while they're going to school. It includes people who went and got a different job and then decided to switch and come back and go back to school. And all sorts of stuff. Anyone who doesn't fall into the traditional high school, college, grad school order. So there's actually a lot of people who are non-traditional students in college and in grad school, and it's becoming even more and more common. So I would say at this point there's not really a bias against it, especially in grad school. If someone goes back to grad school, it is unusual for them not to have taken time off to do something else. But even with colleges, it's completely normal at this point to see plenty of adults in classrooms as well. Where do I want to work after I complete my doctoral degree, and what type of satellites? So there's a couple different options, and the one I've been hoping for and doing all my research for is at Ball Aerospace. Ball Aerospace makes satellites and payloads that are like custom built. So a scientist or the government will come and say, hey, we want you to build something that does this, and this is unique and no one has ever done exactly this before. And then Ball Aerospace says, okay, cool, that will cost this much money and we'll start working on it. And then the people at Ball build their satellite and then hand it back to the government or hand it back to the scientists who request it and say, okay, go launch it. So that's something that I'm hoping to do because I really love unique projects. I don't want to make something that, okay, we make this and we're going to make 1,000 of them, and then we need to update it, make a little change and make 1,000 more. I like everything I'm working on to be unique. So that's why I'm hoping to build unique satellites as a career. I picked Ball Aerospace as my example because they are headquartered in Boulder here, so I wouldn't have to move to work for them. And I've also been doing a lot of research, which you all may, I'll share some of the research I've been doing, because as you all know, it is difficult for women and gender minorities to be treated properly in a lot of STEM fields. There's plenty of situations where you go and you work somewhere and people will ignore you, or people will talk over you, or people will, you'll present an idea and somebody will steal it for their own. Or people will just be flat out rude or sexist or punish you just because you exist. And that's definitely a problem in the STEM fields. So to try to avoid that, I've been doing a lot of research on the companies that I'm looking to work at to make sure that they will actually value me as a person and as an employee. And so that I know that I'm going to be treated like I should be treated, not just, oh, it's just the girl, ignore her. So I've been doing a lot of informational interviews where I will talk to I'll contact one of the women who works at the company and say, hey, I'm interested in working at Ball Aerospace. Would you be willing, and I'm looking for people to interview to understand what it's like working there. Would you be okay if we met up sometime in person or online and I could ask you questions about what it's like working, doing your job and stuff? And I usually try and contact women or minority people and set up those meetings. And I'll usually ask questions. I'll ask all sorts of stuff. Like I'll cover things like, oh, what do you do for your job? Stuff like that. But I'll also ask, do you feel valued? Do people listen to you? Do you think you're getting the same pay as everybody else? Do you feel like you actually have opportunity to move up in your career, or do you think you're stuck where you are? Have you ever been the target of racism or sexism, stuff like that? And those one-on-one meetings are super, super important because I found some companies which I really like, and I think I probably want to work there. And then I've also found some companies that I've been warned away from, and they've told me, yeah, depends on where you go here, but if you go here, you might get a really bad supervisor and your life will be hell. So that is an important skill to work on and an important thing to do when you're going into engineering, to figure out who's actually going to value you and treat you properly.
Glad you mentioned that, because that was actually one of my primary reasons for starting this club to begin with, because I'm in engineering and there are hardly any women at all. And I've been on projects where there have been many companies involved, and even within my company where I've had to lead the project and I've been the only woman out of like 50 people. And I'm like, okay, this needs to change. So this is primarily why we're doing this, is because we want to change the statistics. So women will become more in the STEM field and even STEAM, to where they can do jobs that were primarily focused for men to do, right? But that's great. Thanks for doing that work, because it's really important to close that gap.
Yeah. So when you all start looking for jobs and looking at careers, make sure that you ask around wherever you're going to be working and don't ask the people in charge, ask the people on the bottom, and make sure that it's a place that will actually take you and work with you instead of just demanding that you do everything for them. Have I ever been to a satellite rocket launch? Well, I haven't ever been in person. I expect I probably won't be able to go in person to any of them until my rocket launches in 2024, which I will be super, super excited for. But last week, I got to help with a rocket launch, and it was super cool. So I work at a lab called LASP, the Laboratory for Atmospheric and Space Physics. and it's attached to CU Boulder. So there's a lot of people who work at both of them. And there's a satellite called EVE, SDO EVE, which is the Solar Dynamics Observatory. The satellite is called SDO, the Solar Dynamics Observatory. And an instrument is called EVE, which is the EUV something something something. It looks at the sun and takes pictures of the sun. And it's been up there for, I don't know, 10 years or something now. And as it's been in orbit, there's been stuff that gets on like the lenses, and some of the detectors, like they get bad pixels or something. So over time, its optics just degrade, and there's not really much we can do about it to keep it from actually degrading. But what they'll do is every 2 years they send up a rocket with the exact same detector on it and the exact same optics on it, and it'll go up and it'll observe the sun, and the satellite will observe the sun at the same time. And then when the rocket comes back down, they'll go and pick it up and look at the data, and we will compare how the rocket measurements compared to the satellite measurements. And we know that the rocket measurements are right because we just built that, we just tested it, it hasn't degraded in orbit, or it hasn't degraded over time, so we know that the rocket's right. And the satellite, instead of being up here, might have this type of measurement instead. And so we can calculate how different it is and adjust the satellite's data to match the rocket data. And that's called calibrations. So we can calibrate the satellite data to ignore or to make up for the fact that the optics are degrading. So that was the purpose of this rocket launch last week. And I didn't actually go to where the rocket was launching from, which was White Sands, New Mexico. But I got to sit in one of the assistant control rooms at LASP. And we had my job and my supervisor's job was watching for flares. Because if there was a solar flare happening, that would mess up our data and make the rocket flight useless. So our job was to look for solar flares in some other satellite data. And if it looked like there was starting to be a flare happening, we had to say, wait, hold on, everybody, there's a flare, we can't launch, you gotta wait. And say basically, no, the rocket can't launch, which is a big deal and kind of scary. So we were sitting there, we had a couple different computers set up, and they had a live stream of the data coming down, watching from other satellites that watch for flares. And right as we hit 11 minutes before the launch, which was when the countdown, for real, the countdown clock started going down, and they said T-minus, 500 seconds or something. We're like, all right, cool, this is the actual countdown, time to get serious. And then we turned around and looked at our screens showing the data on if there was going to be a flare happening. And we see the line, which is just, there's a line showing how bright the sun was, and it was just doodling along, doing its thing. And we turned over and we looked, and it had started going up. And we're like, oh no, there's a flare happening. So the rule was, if there was a flare above C5, which is a category of flare, then we had to scrub the launch. And we watched it going up, and it went up to B9, which it goes from B9 to C1, C2, C3, C4, C5. And so it got up to B9, and we're like, oh no, there's a flare, we're gonna have to scrub the launch. And then it stopped going up, and it flattened out, and it started going down. And we're like, oh, all right, we don't have to just say cancel the launch. So next time they checked in with us, we were like, all right, yeah, there was a small flare, but it was small and it looks like it's going down, so it looks like we're good. 5 minutes before launch, we told them, yeah, they could go ahead and launch. So that was last week, and that was the first time I ever participated in a rocket launch, and it was terrifying and exciting and a lot of fun. And actually, I think I've got a video. The people who were running that rocket launch made a video. of the launch, because they actually had two GoPros stuck to the side of the rocket. So they actually have a video of the launch happening. And I'm going to post that in the chat. Let's see, there's a Twitter link to it. This will take a minute. Is there any other questions? Or anything else you want me to talk about? I'd love talking about rockets.
I know, I do too.
Yeah, as you can see, I think rockets are the coolest.
We know we have, I'll invite you. We have where I work, the DirecTV division has a satellite division, and I think they're going to come in November sometimes, and I'll just send you the link just in case you. They have very interesting stories because they've had some explode on them. It can be really interesting and cause a lot of anxiety.
Yeah, that is always a danger, especially for my, like, I'm doing my PhD project on this rocket, and if our rocket explodes, that would be a problem.
Yes.
Yeah. There's a couple different ways you can. Yeah. All right. So I'm posting the video of the rocket launch in chat here.
Oh, okay, great.
So you all can go check that out. For anybody watching this recording later, it is called NASA Riding on a Sounding Rocket, and it was posted July 5th, 2011. I don't know. I will send it out. If this is the wrong video, I will go ahead and send out a link afterwards that you can check out with when the slides are sent out.
Oh, perfect. Thank you very much for that. I have one more question. For me, anyway. So.
Is that the one in the chat?
Yep.
All right. What type of satellites do Earth base stations control? Could you clarify that a little bit?
Yeah, they have like base stations on Earth that have the little microwave dish, right? And they're beaming at some satellites in space. So maybe it's a communication thing, but I was just kind of wondering because most of the satellites you're working on are probably managed through a control tower or control room or something like that.
So every satellite up there needs to have some kind of base station to talk to.
Yeah.
They don't all have unique ones. Usually they share. So you can see in this picture, we've got a big communications dish talking to the satellite up in space. So there's a network. There's a lot of different types of communications dishes. You've got the Deep Space Network, or the DSN, which has 3 giant radio dishes, one in Australia, one in the US, and one in either Europe or Africa. I forget where the third one is. But those are used for talking to interplanetary missions. So they'll use the DSN, Deep Space Network, to talk to our satellites at Mars, or the Voyager probes, which are leaving the solar system now, or the satellites at Jupiter. If you have satellites that are closer, so they're orbiting the Earth, we don't usually need quite such a big communications dish, so we'll use a lot smaller ones. There are some that are just commercially available. You can buy time on them, so you can say, hey, I need 10 minutes every other week when my satellite flies overhead, and you can just buy time to communicate on there. There are also government or NASA ones that if you have the government or NASA has their own system where they say, oh, it's going to be flying over this station, so this station can talk to it. and the government owns it, so the government can say that. Other times, if you don't want to have to buy time on somebody else's dish, you can, and it's worth it, you can actually build your own dish. I don't think this is something that you're allowed to do as an amateur, but like the university and LASP both have big satellite dishes on top of some of their buildings. And those are actually used, there's control stations in the building, and those are actually used to talk to satellites that the university owns that are orbiting. So there's a class at CU that is all about how to run the ground systems and the ground station and communicate to satellites. And they take shifts, and I think it's like each student has to pick a week and be in charge of all satellite communications for that week. And then they go into the system, they use the computers, they program it to say, okay, when the satellite flies over, give it these instructions and download this data. And then the satellite will fly over the university, way, way up in space, obviously. And the dish on top of the university will talk to it and send out the commands and bring the data back down.
Oh, that's interesting to know.
Mm-hmm.
Yeah. All right. Anybody else got any questions for Vicki before we end? I know Sophia and Isabel has a question.
Oh, I'm sorry. They had to jump off.
Oh, did they leave? Okay,
Yeah.
that's why. I know.
You know they would. Absolutely. Absolutely.
Well, if they come up with other questions, I am totally good with them emailing me, and I'm happy to answer them afterwards.
Oh, they love that. Thank you, Vicki.
Yes.
This was so awesome. I thank you.
Of course, we'll always invite you back, Vicki. It was a pleasure listening to your presentation. We learn something new every day, and I'll have all the information in email. The email that you, the Eventbrite people, if you signed up in Eventbrite, I'll send the link to the video, a certificate of participation to your email account within the next day or so. So look out for that, and always stay tuned for our other presentations that we have. But Vicki, thank you very much for joining us today. We hope that you don't get too busy to where you can come back and talk to the students again one day. And we really appreciate you taking your time out.
Yeah, maybe next year, once we actually started building our rocket, I can take pictures and start telling you all how the progress is going.
Awesome. That would be awesome.
When do you finish your PhD?
So we launch in